Time dilation has to do with the fact that different observers moving relative to each other will measure different time intervals between events. To look at this more carefully, let's consider the following thought experiment. Imagine you have a person who is on a moving train, and the person has a flashlight that they turn on and off very quickly to create a pulse of light. This pulse of light moves upward towards the ceiling of the train car, where there is a mirror. So the pulse of light leaves the flashlight, hits the mirror, and comes back down where it hits the flashlight again. So the light pulse leaving the flashlight and then returning to the flashlight are the two events that define a time interval. Now, this time interval, we give the name proper time and have a subscript of P for the time interval. The proper time is the time that's measured by an observer who sees the events happen at the same position. So this has nothing to do with the observer being correct or not. It's not proper in the sense of, well, this is the proper time and everyone else is just fools. No, the proper time is just the time that's measured by an observer who sees the events that begin and end the time interval happen at the same distance from themselves. And it's just a label. It doesn't mean that this person is more correct than anyone else. It's just the label we give to the person who is in this situation. So the proper time, once again, is measured by an observer who sees the events that begin and end the time interval happen at the same position or the same distance from themselves. In this case, the person on the train is measuring proper time. They're holding the flashlight, and when the light leaves the flashlight and when the light comes back to the flashlight, those two events occur at the flashlight, which they're holding, so it's the same distance from themselves. They are measuring proper time. Now, the proper time interval that they measure would be equal to the distance that the light travels divided by its speed. The distance is 2d, d being the distance from the flashlight to the mirror, because it goes up and then comes back down again. And we divide that speed by the speed of light, which is the same in all reference frames. So 2d over c is the proper time measured by the person on the train. Now let's compare this with an observer on the ground. So the observer on the ground sees the light travel a different distance, because not only is the light traveling to the ceiling of the train, but then the train is moving forward at the same time. So the train moves forward a total distance of the velocity of the train times the time interval measured by the person on the ground. And the distance that the light travels, because it also is moving forward, the distance that the light travels is also going to be a bit different. So to see how far the light is traveling, we can consider this triangle here and use the Pythagorean theorem. So this side of the triangle is the distance from the flashlight to the mirror, and so that's going to be d. So there's our d squared plus half of this full path, which is v delta t. This would be v delta t over 2. And so we square that, so that's our a squared plus b squared, and then the hypotenuse of this triangle is going to be equal to the speed times the speed of light times the time interval measured by the ground observer divided by 2, because the speed of light times the entire time interval measured by the observer is the amount of time it takes for the light to go up and then back down again to the flashlight. So this entire path has a length of c delta t, and then we divide that by 2 just to get this part. And so that's the hypotenuse, and we set that equal to the rest, or the other two, the square of the other two sides. So then we solve for delta t, the time interval measured by the ground observer. So if we do that, just do some algebraic manipulations of this expression, we find that we get 2d over c times the square root of 1 minus v squared over c squared, where remember v is the speed of the train. So 2d over c, according to our previous slide, was the time measured by the proper time observer, by the person on the train. And so we see that we get a different time for the light pulse to go up to the mirror and back down again as measured by the person on the ground. So the ground observer, who is not at the same distance from the beginning and ending events. In fact, the beginning event happens here, the ending event happens here, which are different distances from the ground observer. So this is not the proper time observer, this is the other one. So the time measured by this ground observer is going to be equal to gamma, where gamma is 1 over the square root of 1 minus v squared over c squared times the amount of time measured by the proper time observer, the person who sees the beginning and ending events happen at different distances from themselves. So as a result, the amount of time measured by the ground observer is going to be bigger. Gamma is always a number that is greater than 1. So the person on the ground will measure the time interval between the light leaving the flashlight and entering the flashlight as being different from the person on the train. The two observers will disagree on the amount of time between those two events. So this is just to reiterate the important expressions having to do with time dilation. So the person who's not measuring proper time always measures a longer time interval than the person who's measuring proper time, and it's different by this factor gamma, and gamma is always a number greater than 1. So this has important implications. This means that a clock moving past an observer at speed v will run more slowly than a clock at rest with respect to the observer. So if you think about this, what it means is that the person on the ground observer, the person who's not measuring proper time, if the person on the train had a clock on their wall, the person on the ground would see that clock in the train as ticking slower than a clock that they have with them that's at rest with respect to the person on the ground. So they see the events in the train being carried out in slow motion. The person in the train is aging more slowly. They're moving more slowly. Everything involving time is happening more slowly for the person in the train, according to the ground observer. This is really weird, and it seems really counterintuitive. It's not something we notice in our everyday lives. But then again, we're typically not moving near the speed of light or observing things that are moving close to the speed of light. Now, the strange thing is, and the thing that leads to something called the twin paradox, is if you switch your point of view. Now let's imagine that you're the person on the train. If you're the person on the train, you see the ground observer moving past you. According to your frame of reference, according to the person on the train, the ground observer is moving and you are standing still. You are still within your own reference frame. The person on the ground is whizzing by you. Now, if you look at their clock, so let's say the person on the ground has a clock. The person on the train will see the ground observer's clock moving slowly. So since the ground observer is moving with respect to you, the person on the train observes the person on the ground's clock is moving slowly. They see the person on the ground carrying their life out in slow motion. So this leads to something called the twin paradox. Let's imagine you have twins that are the same age. One of them goes on a space journey, and that space journey occurs near the speed of light. So they have a very fast spaceship. They travel near the speed of light. When they return, what happens? Well, according to the person who stays behind at Earth, if they were able to have a very sensitive telescope and see into the window of the spaceship, they would see everything occurring in the spaceship in slow motion. The spaceship is moving with respect to them, and so everything is carried out in slow motion. And so when the person returns, the person in the spaceship returns, they should be younger. Now, according to the person in the spaceship, when they look back at Earth, let's say they also have a very sensitive telescope. When they look back at Earth, they see Earth moving away from them. And so they would see everything on Earth being carried out in slow motion. And so then, according to them, wouldn't the people on Earth have aged less than themselves? So when the person returns from their space journey, which of the twins is younger? So this was known as the twin paradox, and it's actually resolved by something not having to do with special relativity, but having to do with general relativity, which can account for acceleration, as well as inertial frames of reference. So according to general relativity, acceleration also can cause time slowdowns. So if you're accelerating, that slows down the time and it resolves this twin paradox. So the person who's on the spaceship has to accelerate up to that speed, close to the speed of light. They have to decelerate when they get to their destination, and then they have to accelerate again to come back, decelerate again to stop. And it's those accelerations that break this weird symmetry, and it will in fact be the person who goes on the journey because they're accelerating who will be younger when they return than the person who remained on Earth. So let's next consider this question. Suppose you're an astronaut being paid according to the time you spend traveling in space. You take a long voyage traveling at a speed near that of light. Which clock do you want to use to calculate your paycheck?